Welcome to Lecture 6 of Experimental Vibration Analysis. In the last lecture, we discussed the discrete Fourier transform, the DFT, and the fast algorithm to compute it, the FFT, the fast Fourier transform. In this lecture, we discuss how to use the FFT or DFT to estimate two different types of spectra, the linear spectrum and the PSD. The content of this lecture is found in Chapter 10 of the book Noise and Vibration Analysis. This lecture is divided into two videos. The present video is the first video, and here we discuss the linear spectrum and other spectrum estimators for periodic signals. In the next video, we will present how to estimate power spectral density, PSD, with the so-called Welsh estimator, which is the common way to estimate PSDs in commercial systems for vibration analysis. I should point out that these videos explain the estimators we use, that is, the mathematical formulas we use. In a later video, in Lecture 7, we will look at how to use these estimators for practical spectrum estimation. A spectrum of a purely periodic signal can be obtained by a single DFT or FFT. But for most measured vibration signals, however, there is some contamination by noise, which makes averaging necessary. Many times, this is because the signal is not entirely periodic. The vibrations on a reciprocating engine, for example, are often thought of as a periodic signal. But there will most often be some imperfection, so to speak, in the periodicity, due, for example, to the fact that each combustion has slight variations in the fuel mix. There could also be other sources that are random in nature and that contaminates the periodic signal we want to analyze. And finally, there can be noise from the sensor that contaminates it so that it's not a clean periodic signal. In all these cases, we need to average several FFT results in order to obtain more stable values. The averaging we normally apply to spectrum estimates is done in the frequency domain, and of course are done to reduce the variance. That is, for a spectrum component, a peak in the spectrum in the case of periodic signals, we want it to have a stable value within reasonable limits. Furthermore, the averaging is always obtained by averaging the magnitude squared of the FFT results. This is done to ensure that we obtain RMS levels. Furthermore, a window is usually applied to reduce leakage, as we talked about in video 5b. And finally, often we use overlapping to reduce the variance. This will be more discussed in more detail in the next video on PSD estimation. Although we already know that the spectrum we want for a periodic signal is the linear spectrum, we will start by describing the Autopower spectrum. This is because this spectrum is always used for averaging to ensure that the averaged end result will be the RMS of the averages. Remember that RMS is based on the mean of the squares. As you remember from Lecture 5, the Autopower spectrum with RMS scaling is interpreted so that a peak value is equal to the square of the RMS level of a sine at that frequency. To estimate the Autopower spectrum, then, we use this formula. We take the average of m FFT results, each based on the windowed DFT results, uppercase X sub Wm. We average the magnitude squared of each frequency bin of this DFT. And finally, we apply a scaling factor, uppercase S sub A, to make the values scaled to the RMS level squared. This scaling factor, S sub A, we obtain in this way. You should remember from Lecture 5 that scaling the DFT magnitude by 2 times A sub W over n produced a DFT spectrum with the amplitude of a sine being correct, provided there was no leakage. Now the factor 2 comes from this double-sided scaling, and A sub W over N came from scaling the DFT. Now we need to divide those numbers for RMS scaling by the square root of 2 to ensure that we get the RMS level instead of the amplitude. We then square this scaling factor, since here we want the Autopower spectrum. Thus we obtain 2 times the square of A sub W divided by N squared. And this applies to all values of K larger than from 1, 2 and up to N half. For K equals 0, however, as is shown here, we don't apply any double-sided scaling, as the 0 value only occurs once. And there is no RMS level for a DC either, so we just simply use A sub W squared over N squared. The amplitude scaling factor, moreover, is A sub W, is defined simply as the block size n divided by the sum of the window values, as we saw in the previous lecture. And for a Hanning window, this value, A sub W, is exactly 2. In many cases, we have 2 signals for which we want to estimate the phase difference, the phase angle between the 2 signals. We do this by the cross-power spectrum. This is the best way, and really the only way, to obtain the phase difference between 2 signals. And it's obtained by averaging the product of the one DFT of the signal Y and the complex conjugate of the DFT of the other signal X. The averaging process is similar to the one we used for the Autopower spectrum, with the same scaling factor, etc. You should note that the angle of Y times X complex conjugate equals the angle of Y minus the angle of X, which is exactly what we want when we want the phase difference. We now have the intermediate results that we need in order to estimate the linear spectrum. So we obtain the linear spectrum simply as the square root of the usually averaged Autopower spectrum. We then have a spectrum, x hat sub L, in which a peak value is interpreted as the RMS of a harmonic component at that frequency. Note that the linear spectrum has no phase. In some cases, we want a linear spectrum to have a phase relative to some other signal. We can then use the phased spectrum, which is obtained by combining the linear spectrum with a phase from a cross-power spectrum. Thus, the phase spectrum of the signal X that we denote x hat sub P is the linear spectrum x hat sub L times e to j phi hat sub xv. Here, the angle phi hat sub xv is simply the phase of the cross-power spectrum A sub xv, where V is the phase reference signal. Phase spectra are very useful, for example, for operating deflection shape measurements, or ODS measurements, that you can read about in chapter 16 of the book, or in some rotating machinery applications, which you can read about in chapter 12 of the book. This concludes the present video. You should now proceed to video 6b.